Okay, so
Yes, so I went through this. All right, thank you so much, Mahmoud. So we're going to start with the problem statement. So red light running is one of the leading reasons behind crashes at signalized intersections, and it is the main cause of a significant number of fatalities. So red light running is associated with more than 8% of fatal crashes at the signalized intersections. Over a period of 4 years, ranging from 2014 to 2018, there were more than 4,000 traffic fatalities and over 200 pedestrian bicycle fatalities involving a red light violation. In 2018 alone, around 800 fatalities were reported due to red light running, with estimated 139,000 injuries. One contributing factor to these types of crashes and violations in the first place is the existence of uncertainty as the drivers approach what has been termed as a dilemma zone. This zone is where drivers are uncertain of whether to stop or advance to clear the intersection successfully during yellow light. Drivers' uncertainty in a dilemma zone may either result in rear-end collisions because of sudden brakes or red light running violations followed by right-angle collisions. A potential solution to this problem is, which is the focus of our study, is the connected vehicle red light violation warning application. Red light violation warning is expected to reduce the crashes between red light runners and cross traffic due to increasing drivers' awareness of the signal status as they approach a signalized intersection, which will reduce the uncertainty in the driver's behavior, particularly in the vicinity of the dilemma zone. So how does this application work? Basically, the vehicle onboard equipment of the red light violation warning application receives signal timing and map data from the roadside equipment. Now, combining this information with the vehicle-specific information, such as the speed and distance to the stop bar, the red light violation warning application assesses the probability of the driver violating an upcoming red light. According to this probability, the onboard equipment of the application sends messages in forms of either advisory alerts or warnings to assist the driver into making the correct decision in the dilemma zone and avoid the red light. In order to study the benefits of this application through simulation, correct calibration is key to accurate simulation. One main parameter in modeling and simulating the red light violation warning application is the driver's behavior in the dilemma zone, which is characterized by the probability of either stopping or going at the instance of the yellow light. So one main goal behind our study is to calibrate the mentioned driver's behavior and showcase its impact, the impact of calibration, on the validity of the red light violation warning simulation results. As you will see later, we will provide a method for calibrating the driver's behavior based on real-world data. Our second main objective is to utilize this calibrated model to evaluate the benefits of red light violation warning application. So we use the simulated vehicle trajectories from VSIM's calibrated model to identify, classify, and evaluate the safety benefits of red light violation warning application based on utilizing the surrogate safety measures assessment, surrogate safety assessment model, which is developed by FHWA. Next, we will go over the literature review with Thodsapon.
Thank you, Kamar. So the literature review that we went through for this study are real-world drivers' behavior in dilemma zone, and also some of the studies on the implementation of the red light violation warning applications. Next, please. So most of the studies which is related to red light violation warning application, they have relied on the field observations and also driving simulators, just like the study conducted by in 2013. This study was basically based on a field test, and also another study done by Nakamura in 2016. This one, they used a driving simulator to examine drivers' behavior. And the most recent study that we found that was done by Banerjee in 2020, they analyzed the effects of red light violation warning on the driver's braking behavior. Next, please. Next, please, come on. So another type of studies that we have looked into was also the real-world driver's behavior regarding the probability of stopping of the vehicle and the travel time to the intersection measured at the start of yellow time. So there are a couple of studies that done for this particular topic, and the most recent one that we found was done by Gates in 2007. this study basically updated the two models that were proposed by the Shefa and Mamasani in 1981, and another study by Van der Oors and Romink in 1986. And next, please. And we will talk about what are those parameters. And one of the objectives that we were saying, that the Kamar was saying, that we want to get the model, basically get the model ready to assess the safety impact or the mobility impact of the red light violation warning application, and then how we recorded this red light running violation application in this sim. Next, please. So this is the logistic model in InvestSim. It determines the probability that a vehicle will stop at an amber light. So in the driver behavior, particularly in signal control behavior, there's a behavior related to the amber indication, how vehicle reacted to the onset of, how the vehicle reacted to the yellow signal. So yes, as you can see, there are three parameters here that we calibrated, which are alpha, beta 1, and beta 2, and two important variables in this logistic equation are the vehicle speed and also distance to the intersection measured from the vehicle. So in short, by using the default values of these three parameters, alpha, beta 1, and beta 2, the resulting violation, red light running violations will be 0. So that's why this is also the first objective of the study, is that we want to calibrate these three parameters based on the real world probability of stopping data that we have. So again, if it is the best if we have the local data available, but now but the purpose of this study is to show that the framework of the calibration, how if one wants to assess the impact of this application, how can you start? This is the framework that we want to stand up. Next, please. And again, basically, we adopted the probability of stopping that was done by Gates study here. Next, please. Then, in order to find the best combination of those three parameters, we use the nonlinear programming to optimize to solve the problem. Next, please. And this is the algorithm that we code in InvestSim. In short, basically, this algorithm it begins when it continues to check the signal status in InvestSim. So if in the real world, that would require spec data. So it begins when the remaining green time is less than 5 seconds. This is just to make sure that some vehicles this is just to make sure that some of the vehicles that they are in 5 seconds, it's like if they are in dilemma zone, they can clear really intersect safely. And also if the remaining green time, remaining amber time is higher than 0, so that means the current signal time is amber. This application will check whether the vehicle is in the communication range. If yes, then the approaching speed and distance to the stop bar will be measured. Then the algorithm will compute the time to clear the intersection of the vehicle. If the time to clear the intersection is higher than the remaining amber time, and also that if that vehicle is in the dilemma zone, the warning message will be sent to that driver, to notify them about the potential in running the red light. Then Mahmoud will be talking about the result that we studied.
All right, thank you so much, Thodsapon and Kamar. So now, since we explained the entire methodology framework, we will go quickly through the results and what we found so far, the results from the simulation model and the results from simulating the connected vehicle application. So we will talk about the sensitivity analysis, we will talk about the calibration results, and we will talk about the benefits of the application. So first, the sensitivity analysis is basically to figure out the impact of each parameter that Kamar talked about, the alpha and beta 1 and beta 2, the impact of each parameter by itself on the simulation model. And thankfully, we could be able to, to conclude that whatever the results that you will find in the PTV VSIM simulation manual is exactly the same that we found from our ComScripts results. So basically, alpha didn't have much impact on the simulation model. However, beta 1 and beta 2 were positively correlated with the number of stops decisions and negatively correlated with the number of go decisions, which means that if you increase the value of beta 1 and beta 2, you will most likely you will have we're negatively correlated with the red light runnings. The more you increase the beta 1 and beta 2 values, the higher the likelihood of a vehicle that it will stop on amber when the driver see a yellow light, and the lower chances of running a red light, which further signify the results that you will find in the manual, in the VSIM manual. The results from the nonlinear programming optimization found that the best combination that you can input for alpha, beta 1, and beta 2 is alpha equal 1.6, beta 1 negative 0.1, and beta 2 is equal to 0.043. And again, this combination was based on the best combination on our case study intersection. For the audience who are listening to this, that doesn't necessarily mean that this combination will work the best for you. You need to collect your own local data. You need to calibrate your model based on your own local conditions. So, however, what we are showing here is the best combination for our own scenarios. So if you could really see here in the figure the difference, we wanted to show you the difference before and after calibration. What was the impact of this calibration in the simulation? So the blue line is basically the trajectories that we got from the simulation model, and the red line is basically the trajectories for real world data. So since before and after calibration, the real world data should stay the same, you will see that the impacts of calibration before and after with the simulation trajectories. Before calibration, you could really see here on the left-hand side, the white area in the middle is basically the errors that you will get if you kept the default VSIM parameters without calibrating to your own local conditions. However, after we got the combination of alpha and beta 1 and beta 2, we were able to reduce the sum square error from 9.75 to 0.03 at the optimal iteration, which is basically you have VSIM was successfully able to 100%. I'm not gonna say 100%, but 99.7% perfect to simulate a real world probability of drivers on stopping on amber. So next, please, Kamar. So we used, Kamar, could you please go next? So we used two surrogate safety assessments, two surrogate safety measures. We used the right angle conflicts and the rear end conflicts, which are basically the two conflicts that will mostly or will highly be impacted by a red light running application. Those two types of crashes, the right angle crashes and the rear end crashes. So we used, of course, the surrogate safety assessment for testing this. And you could really see here also we reported before and after calibration the impacts on the red light runnings and the right angle crashes. Without calibration, you could really see the blue line, which is before calibration on your left-hand side, is basically we had a 0 red light runners in the simulation model. However, after we inputted the correct alpha, beta 1, and beta 2, we could really reduce the red light runners from 9.6 vehicles per hour to almost 0, with a utilization rate from 0% to 100%. The utilization rate is basically the market penetration of a connected vehicle multiplied by the compliance rate of drivers. And on the right-hand side, you see that the results of the right angle conflicts. We could decrease the red light violation warning application is able to reduce the conflicts from 9.4 conflicts to 5.5 conflicts. Then again, next please. We will talk about the rear end collisions before and after calibration, and also with increasing the utilization rate for a connected vehicle from 0% to 100%, we could able to reduce the rear end crashes or conflicts from 29 conflicts per hour to 14 conflicts per hour. And with that, we will turn to the next application, which is the stop sign gap assist application in a connected vehicle environment. And I'm going to give it to Kamar to tell us more about the introduction of the application.
Thank you, Mahmoud. So similarly, I'm going to start with the problem statement. So a two-way stop-controlled intersection aims to improve traffic operations for the major street. So vehicles from the minor approach who are supposed to yield to the conflicting traffic are allowed to enter the intersection once acceptable gaps are determined to be available by drivers on the minor approach. However, two-way stop-controlled intersections contribute to approximately more than 40% of fatal crashes. Mainly, the reason behind these types of crashes can be attributed to drivers' misjudgment of the presence of a sufficient gap in the conflicting traffic, their failure to yield the right of way to the major road, and inadequate or obstructed side distance. So a potential solution to this problem is the stop sign gap assist connected vehicle-based application. It is designed to provide assistance to drivers on a minor road and allow vehicles to safely traverse or enter a major approach. So this application supports drivers' crossing decisions by providing also advisory messages, alerts, or warning messages to vehicles on the minor road with the approaching vehicle information on the vehicle road. Now, similar to other vehicle-to-infrastructure applications, previous studies reported that stop sign gap assist application can utilize two decision support interface alternatives, the driver infrastructure interface and rival vehicle interface. So with that, the goal of our study is mainly to investigate the use of microscopic simulation models to quantify the potential benefits of a stop sign gap assist connected vehicle-based application, considering both mobility and safety impacts. We also used VSIM as a microscopic simulation tool to model the stop sign gap assist application and to assess its impact on traffic performance at an unsignalized intersection. So similarly to the red light violation warning application, we use the vehicle trajectories data output from VSIM to evaluate the safety benefits based on surrogate safety assessment model, which was also developed by FHWA. Now with that, I'll hand it over for Thodsapon to go over the literature review and the model.
I'm sorry, Kamar, maybe we are like running a little bit of time, so we can go quickly through the slides.
Yes, sure. Yeah. So, so the literature review that we went through was related to the real-world drivers' behavior, particularly at stop control intersections, and also the previous studies on the assessment of the SSGA application. So, well, quickly that. Okay, next, please. So this is the distribution that we. This is the gap time distribution that was done by the study of this Ayanaki, John, and Yi in 2002. Basically, we adopted this model and then we calibrated this gap acceptance in VSIM rather than using a constant value of gap time. I think when one wants to assess the impact of this application, I mean SSGA, we want to see the importance of using this gap time distribution rather than a constant value. Next, please. So very quickly, next, please. So the intersection that we coded in VSIM was a basic four-way two-way stop control. Next, please. And again, the model that we adopted was by this Ayanaki study. Next. Then this is the SSGA algorithm that we coded into VSIM. Very quick, if anyone wants interested, you can look at the paper because we're running out of time. So Mahmoud will go over the results about this paper.
Thank you so much, Thodsapon. I'm sorry that we wasted like some minutes in the beginning, so we will go quickly over that. And again, as Boy said, if you guys need like more information or more details, like just feel free to come back to us or check the proceedings on the TRB website, and also that stop sign gap assist have already been accepted for publication. So you can stay tuned for a couple of weeks. You will find the entire paper published online. So Kamar, can you go next, please? So we will go quickly over the analysis and the results of the capacity and the calibration results. So here we showed you in this figure we reported the VSIM with using a real-world gap acceptance distribution, and we reported the VSIM with using a default 3 seconds gap time parameter, which is basically the default gap time that you will find in a priority rule. And also we reported here the several gap stop sign gap assist utilization rate ranging from 10%, 50%, 70%, 100%. And then we further validated this model using the HCM, using the HCS software. So as you could really see here that, again, VSIM is 100% able to replicate a real-world gap acceptance distribution. However, you need to model your correct parameters in the simulation. And going back again to the point that we started, that VSIM is 100% can give you a risk-free environment that you can, it can help transportation agencies in the pre-deployment and the post-deployment of connected vehicles. You can use the simulation in a software in the loop and a hardware in the loop. It gives you like really a variety of scenarios that you can utilize the simulation package. I don't want to sound like, you know, making commercial advertisement, but really I found the software very helpful in our studies. So you could really see that before and after calibration with using the default 3 seconds gap time parameter in VSIM, we will have like, it underestimates the real world gap acceptance distribution. I'm sorry, it overestimated it. But once you input the distribution of the priority rules as a gap acceptance as a distribution instead of a constant parameter, you could achieve the real world driver's behavior. And next, please, this is the last slide. We will talk about the safety benefits of the application. So we simulated, as Thodsapon was saying, that we simulated the stop sign gap assist application. We used 4.5 seconds as a design threshold that will give you the alert after 4.5 seconds gap time, or 6 seconds, or 7 seconds, or 8 seconds. So we modeled the 4 gap time thresholds in VSIM, and the result, and also we reported the safety benefits in terms of the right angle conflicts. And you could really see that as long as the minimum gap time utilized in the simulation model increase, you will have a less right angle conflicts. However, like this, we found you know, a trade-off. So here we are talking about 2 benefits of the application. We are talking about safety benefits and mobility benefits or capacity benefits. If you input the time gap parameter, if you put like less 4.5 seconds, for example, basically you are releasing more vehicles in the intersection and you are creating more conflicts. However, you are increasing the capacity of the minor road. But if you increase the gap time parameter to 7 seconds or 8 seconds, obviously you are improving the safety of the intersection. However, you are decreasing the capacity on the minor road. And you could really see here the number of right angle conflicts. It fluctuates basically from 11 conflicts to 16 conflicts when we used the opposing traffic from 250 vehicles per hour to 500 vehicles per hour. However, once you have like with a higher flow rate of the opposing traffic to 750 vehicles per hour, the number of conflicts increases with the utilization rate, again, due to the assumption that more conservative drivers will utilize the service and will use shorter gaps. So thank you so much. This is pretty much it for having us and for hosting us. Can you go to the next slide? I'm sorry, Kamar. So feel free to send us an emails or reach out to the Lehman Center for Transportation Research. And again, this study was done by under the supervision of Professor Mohammed Hadi, the director of Lehman Center for Transportation Research at Florida International University.
Thank you for joining today in this session, and I would like to thank the PTV group for giving us the opportunity to present our work. Are you hearing me? I mean, is the sounds okay?
Sound great.
Okay. So this is Rajib. I'm a PhD candidate at Florida International University, working with under supervision of Dr. Mohammed Hadi for the last 3.5 years, and I'm expecting to graduate in this semester in April 2021. So here today I'm gonna present our work, the recent work, which is the integrated approach for optimizing traffic management plan during freeway incident. So actually, why we did this study? So the reason behind is like in the left hand side in the figure, you can see when there is an incident in the freeway traffic, the most common method actually the agency used is the diversion. Basically traffic generally the driver to cross this incident location because of the reduction of the capacity in the road and also for the long queue. So when they divert to the arterials or another freeway or whatever the alternative routes, if it is the arterials, they face the signal control. So what actually happened in the existing study, in all the existing study, mostly studies and also the for the coordinated operation, they consider the fixed route. Basically, when there is an incident, they think like the immediate upstream off-ramp is the one traffic generally used for the diversion. But for observation, we saw like this is not actually true. And it is not as simple as that. There are many other factors like the traffic and also the day of time period, and also the other conditions, they actually impact the situation. And because of this, in many cases, traffic actually started diverting way before from the incident location. So this is basically a dynamic phenomenon, not a fixed system. But all the studies actually right now is considered as a fixed system. And the next one is to implement this coordinated idea, like the integrated corridor management, you can say, or the coordinated operation between the freeway and arterial when this kind of diversion occurred. To implement this idea in the field, agency need to run the online simulation. So many agencies doesn't have that much resources to implement this idea in the online, to run the online simulation in real time, and also to run this unit the extensive data. But for our study, actually, we try to do is use as little as possible data to do this, and also we try to implement idea in a way so that agency doesn't need to run the online simulation. The third one is the signal control. So when traffic hit the arterial road, so they face the signalized intersection. So to accommodate this demand surge, we need to introduce a new signal plan, because the currently existing signal plan, which is mostly the time of day plan-based control system, which cannot able to respond to the variation of the traffic for this instant demand surge, because all this time of day plan-based system developed based on the normal condition. And the second one is only a small number of intersections have the adaptive traffic control system, but the performance of this adaptive traffic control system still needs to be evaluated when there is a long queue or this sudden demand surge. So in our study, actually, we address all this condition, all this dynamic phenomenon, and we developed a method so that the agency can easily implement this idea in the field. So in this solution, our solution actually included basically three main idea. One is three main methods that includes one is the prediction of the scenarios in the alternative routes. So what kind of scenarios actually when traffic is started diverting the alternative route, what kind of scenario actually occurred in the alternative routes, that using the machine learning and also the clustering analysis. And the second one is the estimation of the effect of the traffic demand on the alternative routes. So in this one, basically we use the multi-resolution modeling, which includes all three parts of modeling, the macroscopic, macro, meso, and microscopic simulation modeling, to estimate the traffic demand in the alternative routes. And finally, actually, after identifying the scenarios, for all the scenarios, actually, we developed the signal plan, a special signal plan, so that it can address all these demands. At the same time, also it doesn't deteriorate the performance of the overall performance of the networks. To do this, we use actually multi-objective optimization, and here we use actually the vsim-com interface to develop the signal plan. So one of the important aspects of this our study, actually, we use the multi-resolution modeling framework that I previously mentioned. In this multi-resolution framework, we use the cube software and then PTB, VSIM, and VSIM. So what actually we did in our case study, which is in South Florida, that is the planning model is developed on using the software cube. So they developed this software cube. So we need from the planning model, we extract the sub area as well as the OD matrix. So initially, actually, for this sub area and OD matrix, we ran the highway assignment module of the cube to get the OD matrix for this sub area. And then, thanks for the PTB group, like the PTB VSIM has the ability to import the data from the cube software. So actually, after running the highway assignment module in the cube, Then we imported the OD matrix data and the network in the BSIM platform, the PTB BSIM platform. So in PTB BSIM platform, basically we imported here to run actually the mesoscopic simulation model. So why actually we need the mesoscopic simulation model, and especially in mesoscopic simulation model we address the new features, actually the simulation based assignment that available in PTB BSIM. So in BSIM we use the simulation based dynamic assignment, which is dynamic assignment that we utilize this method because it has the ability to address the dynamic phenomenon in the network. So in simulation based running the simulation based assignment for this changing condition, we need to actually calibrate the model. So we need to calibrate the model for both the normal condition as well as for the incident condition, because we need to measure the traffic demand in different alternative routes during any instantaneous situation. So for any given incident condition. So to do this, first we in the next slide I will talk about more about the calibration part, but the third part actually we did, which is the microscopic simulation. In microscopic simulation, actually we imported that BSIM route and data into our microscopic simulation model in BSIM, and in BSIM we actually run the multi-objective optimization using the COM interface to get the optimum signal plan for these scenarios. And also we use this microscopic simulation to evaluate our plan as well. So one of the challenging part is the calibration of the SBA model, and which we did for both for the normal condition as well as for the incident condition. So for the normal condition, actually for both condition, actually we use the data. We use basically the one of the data we got from the street light, which is we street light data for the OD path-based traffic OD data as well as the travel time for both normal condition as well as also for the incident condition. And also we got the we calculated the reduced traffic count data and also the turning data. So after getting all these data, basically we calibrated the SBA model for the normal condition, and we see we use the criteria, which is the Federal Highway Administration has the set criteria, like we have to have the traffic count and travel time less than 15%. So when we see this the criteria is met for the normal condition, then we actually put it then we calibrated the model for the incident condition. Incident condition, we actually put the lane blockage and also the incident duration in the freeway, so that traffic actually starting diverting. So to do this in SB, actually it is not possible to directly reduce the capacity. So to do this, actually we use the time bearing and the critical gap time as well as also the reaction time. We change this so that the capacity comes to as close as possible. And in here we actually for the standard we use the ACM capacity for different incident condition, 1 lane blockage, 2 lane blockage. So we compare it for the ACM. And then after calibrating this model, this ACM, then we run for the different scenarios. We actually come up with the 11 scenarios. For all the scenarios, actually we but overall finally we developed the signal plan for 5 scenarios. So in the calibration result, you can see this is this calibration result is for the incident condition basically. So you can see these 3 routes, which is very important for the diversion. And these 3 routes, you can see that for the traffic counts, it's like less than the 10%. So it's criteria. For time, it's little bit for 2 to 3 lane blockage, it's little bit higher than the 15%. It's around 16%. But for all other cases, it satisfies the criteria. So after doing this calibration, and we ran the SBA, and then we got the route level traffic demand for different scenarios, and then we imported it to the BSIM for optimizing the signal plan. So for optimizing the signal plan in BSIM, actually we use the multi-objective optimization, and here our main goal was to minimize the delay and maximize the throughput. So in the network, in the network as well as in the diversion route. So in the network and diversion route, we try to minimize the delay. At the same time, also we try to maximize the throughput in the network. And here, so for different signal plan, and for solving this optimization problem, basically we use the SSGA2 two multi-optimization algorithm, which is a part of a variation of GA, genetic algorithm. So we use this algorithm and we use the BSIM-COM interface. So what actually we did basically, we wrote the algorithm separately, and then we ran through the COM. We access the BSIM simulation, and also so through accessing the BSIM, we actually, after running the algorithm, that data actually we put back it to the BSIM, and then BSIM run the simulation, and then we get the output from the BSIM and then put it back to the algorithm again. So it's like kind of like loop, and we did for like till our estimate criteria met. So after doing this optimization in the BSIM, then we finally developed our plan for this one, for scenarios. Here the result I shows is for the 5 scenarios, but overall actually we found like our clustering analysis, we found like there is 11 scenarios. So these 5 scenarios, the result you can see here is for both the overall network as well as also for the diversion route. So in the left hand side you can see that like for the overall network, although the improvement is little bit less, but for the diversion route it's high, but it didn't deteriorate the performance of the overall network. Maintaining the performance of the overall network at the same time is improve the performance for the diversion route. So it's actually encourage the drivers to actually divert and using this route, so that the overall congestion of the whole network in the corridor actually reduce, and which is actually the theme of the integrated corridor management, which is very popular throughout the country, across the country now. So, and you can see the improvement is for more than 60% increase of the throughput. Like the delay is like more than 10% for different scenarios, and and some of the scenarios it's like too much congestion. For these cases, like the improvement is not that much, but still our plan is able to improve the scenarios. So the advantage basically to deploying for our method is like agents only need to know this plan and also the scenario, and for the scenario measurement basically they need to know only the travel times, because our whole methodology is dependent on our machine learning methodology depends on the travel time. So agency only needs to know the travel time data. They all, and most of the agency actually already have this travel time data from Bluetooth or from third party, so they can just only knowing the travel time, they can and scenario is not the travel time. So if they know the travel time, they will know the scenarios, and then based on the scenarios they just need to switch on the new plan, the plan we develop. In this case they don't need to run any online simulation or anything, and the whole methodology is dynamic because it's instantaneously predict the travel time. Our methodology, which actually this is the last part of this work, but in the previous part of the paper actually we developed a machine learning model using the LSTM, and in that model basically we predict the travel time for after the incident, we predict the travel time from 15 minutes to up to 90 minutes. So this is, so whole methodology is kind of like a proactive method, so they don't need to wait till the constraint is happening. Just after immediately incident occurred, they will be able to predict the scenarios, and they will be able to predict the travel time in the alternative routes, and then based on this travel time they will be able to know, okay, this route will be going to be considered that much, and this is the scenarios, so like 25% increase of travel time. So that's the scenario, and for this scenario the suggested signal plan is this one. So they just need to input these travel scenarios, the signal plan. So that's all from my presentation, and the paper link is available here.
Hello everyone, this is Denis Monyo, a transportation engineer at Peters and Yaffe. I graduated from the University of North Florida, and I would like to take this opportunity to welcome everyone to my presentation titled Deploying Connected Vehicles to Mitigate Secondary Crashes on Freeways, a Microscopic Simulation Approach. So, what are the secondary crashes? Secondary crashes can simply be defined as any incident that is an outcome of a prior incident within the same vicinity of the prior incident. And also, secondary crashes can also occur on opposite traffic due to rubbernecking phenomena. And various road incidents may cause the occurrence of secondary crashes, such as road accidents, vehicle breakdown, speed, load or debris, and inclement weather. So how big is the problem? Studies have shown mobility and safety problems resulted from secondary crashes, as you can see here. And so quickly you can see some of the factors that lead to occurrence of secondary crashes, including weather, primary incident attribute, road geometric attributes, and real-time traffic conditions. So traffic incident management agencies have considered different strategies so far to prevent occurrence of secondary crashes. For instance, strategic allocation of incident responders to hotspot locations, the use of variable incident, variable speed limit, and also we have advanced warning messages. So here you can see stuff like dynamic message signs and smartphone applications, also connected vehicle technologies, because this can disseminate incident warnings at the same time suggest the best actions for drivers to take. So to mitigate secondary crashes, as I said, secondary crashes, this is a time-sensitive process. Like if the crash has occurred, you have to be very quick to disseminate that information to upstream drivers so that you can mitigate them to be trapped in, to experience another accident as an outcome of the primary incident. So this is like a time-sensitive process. But the use of the method that I've mentioned before, there is a lapse of time between when the incident occurred and when upstream drivers get the information. So this lapse of time may increase the likelihood of secondary crashes. But on the other hand, the use of smartphone applications and connected vehicles technologies have potential to disseminate traffic information in real time more quick. So having seen challenges of mentioned strategies like aforementioned strategies, let's see the side of connected vehicles technologies. So connected vehicle technology, as we know that it's just enhanced capabilities of vehicle-to-vehicle communication and vehicle-to-infrastructure communication. So these, unlike other strategies, this technology can have potentials for slashing the delay in disseminating advanced messages to drivers when an incident occurs. So through automatic incident and quick dissemination of incident-related information, so that itself can help slashing the delay or relaying information. So this video clip shows the example of vehicle information that can be shared in severe environment, including location, speed, as you can see, direction and advisory messages. So this can be useful in mitigating secondary crashes by sending a notification, such as a hard braking ahead, where a driver can reduce his or her speed, possibly to avoid the crash ahead. So due to its low latency and security capabilities, dedicated short-range communication has been mentioned suitable means of communication for transportation safety applications. And studies have shown various mobility and safety benefits associated with CV technologies, as you can see. So safety analysis, observational models, this depends on historical crash data to assess the safety of facility. But on the other hand, we can use surrogate safety measures such as traffic conflict analysis and microscopic simulations that to give as an alternative approach to observational models in a situation where crash data are limited or when evaluating the potential safety benefits of certain modifications before their implementation, for instance, CV deployment. So this is the main objective of my study, is to quantify potential benefits of CV technologies at varying market penetration rates in mitigation of secondary crashes. So here I use traffic conflict analysis as a surrogate measure for secondary crashes. So I have a communication plan that is needed for proper and efficient relaying of this primary incident information. So this communication plan will reduce the risk of secondary crashes. So as we know, after incident occurrence, there should be incident detection, incident verification, and processing of information and advisory messages that need to be disseminated all the way to other motorists. So this can be done through DMS and connected vehicles technology. So I just used connected vehicle technology. As I showed you in the last slide, there is a couple of means to disseminate information, but in my case, I want to use DMS. I'm going to use CV. So under CV environment, information can be conveyed from detection all the way to motorists approaching the scene. So this shows potential of connected vehicle communication to quickly disseminate incident-related information, therefore reduction of the likelihood of occurrence of secondary crashes. So this figure shows the algorithm that I developed, which uses the process, which used it to process advisory messages to be disseminated to motorists during an incident period. So the algorithm's objectives was to provide speed, lane change, and/or detour advisory message to drivers upstream of an incident location. So this was, the target was to mitigate the occurrence of secondary crashes. So the algorithm requires traffic parameters as an input for that to, come up with appropriate advisory message. The red box here, this was used. This part of algorithm was used to enhance the detour advisory, and the red box here you can see it shows like travel time was used as the performance measure, and it compared the travel time along the main route and the detour. So whenever the travel time along the detour was shorter compared to the main route, the vehicles were the connected vehicles were advised to consider that route, the detour route, for that matter. So here's my methodology. So this network considered the study area considered the segment of Florida's Turnpike network that passes the District 4 in Broward County. So as you can see here, the legend, it shows the incident location. I modeled my incident right here, as showed in the legend that you can see, and the detour and the main line with their respective speed limit are shown in this slide. So my network was a fixed lane, like 3 lanes in each direction. It's about 8-mile segment, and the site was chosen along the Turnpike network, Florida Turnpike network, because of crash count experienced in the year 2016. And the detour is Lyons Road. It has a 4-lane, and it's about 4-mile length. So this was used to divert traffic, all the way to Lyons Road and back to Turnpike network. So these are data sources. These are the main data sources used in this study, Florida's Turnpike. This provided like the primary model that was used to for this study. We modified the model. I added the detour and the calibration process. Also, Signal 4 analytics was used, as I mentioned, to retrieve crash history along the network, so that to come up with a section that I was using as the study corridor. So this is like a general flow of my study. I won't go like in every stage, I think, because of time. So the first thing was to create and calibrate the VISIM network model and to model primary incident. I'll show in the next slide how I did some of these stages right here. And these are some of the scenarios that was considered in my study. And the scenarios were considered because of to consider the effect of traffic volume, and that's why I had AM, pre-peak, and post-peak, and peak period, and also I varied my bucket penetration rates, and I just modeled the incident in outer lane and inner lane. So this was just to vary the situation of a primary incident to see the effect in the occurrence of secondary crashes. So the study leveraged CV applications, and these are the sum of advisory messages that was considered, like lane change, advisory warning, and also the detour advisory, and the speed advisory. So these are the kind of advisory messages that was considered in the vehicle to infrastructure communication along the selected corridor. So here you can see VISIM capabilities. The VISIM has several customizable features, as we know, and it provides add-on application, API such as a COM, so which this provides user with the capability to incorporate their own applications. So in this StatCom API was used to access vehicle attribute and to integrate CV applications during the runtime. And we had some couple of assumptions like 100% compliance rate, no data loss, and only the northbound traffic was considered during this study. And for modeling the incident, we used to add vehicle at a link at a certain time and position with a 0 speed limit to mimic the blockage, the lane blockage. And for that case, it just acted as my primary instance, like to block the lane. So depending on whether I wanted to analyze the outer lane or inner lane blockage, I apply this function to introduce the lane blockage. So the RSU functionality was just applied in my simulation environment by a get by location function. So this was used to retrieve the vehicle data, and after processing of kind of information to be disseminated to upstream vehicles, the vehicles within range were just receive the information that was processed by algorithm through this get by location. So every vehicle that was within range was just received the processed kind of message respective to their location relative to incident location. So here we use the event-based script. So here I use the visual-based decode to replicate communication plan that I discussed before and CV applications, and to manipulate driver behaviors to increase their safety. So that was led to really time changes in vehicle parameters during the runtime. So let me go quickly to START framework. The motivation of this study was to mitigate secondary crashes, and we derived the START concept, and then we developed a communication plan on how we can just relay those information from primary incident all the way to upstream or upcoming vehicles that approach the incident scene. We use COM API to simulate CV wireless communication in the VISIM interface, and we did some couple of scenarios in there. And then safety analysis was done by using SSAM, and here I used the positive cross-range time as well as time to collision as my threshold to define, as surrogate measures to define possibility of conflicts. And then we obtained conflicts as a rear end and lane change conflicts, so that was the output of our safety analysis state. And statistical analysis was done finally to check the significance of changing CV market penetration on reducing conflicts. So these are some videos here, just show the way you have the green vehicles there are just the vehicles with like connected vehicle. So whenever I'm increasing the penetration rate, I'll have more green vehicles in there. They can just take lane change, they can reduce their speed, and they can take a detour. I don't think if you can see that clearly, but those are the kind of messages that I was advising CVs along my network just to consider. So as I said, trajectory files from VISIM were just imported in SSAM and define some threshold in there to get lane conflicts, traffic conflicts as a safety analysis part. So quickly, let me go to results and findings. We had a pre-peak and post-peak. This reflected the lower traffic volume period and post-peak and peak period. This, as it reflected a higher congested period. So during the AM period, these are the results. Quickly, these are the number of conflicts against the CV penetration rate, and it just represents the inner lane blockage and when the outer lane was blockage. And the introduction of CV reduced the number of conflicts. As the market penetration of CVs increased, you can see there was a relative decrease in number of conflicts. And in all scenarios, the rear end conflicts were more prominent than the lane change conflicts. And the results show a higher number of conflicts in the outer lane scenarios than the inner lane blockade scenario, because I think this is due to the weaving, the merging and diverge maneuver close to the incident location that we selected in our study. So when the outer lane was blocked, we experienced a lot of conflicts more than when it was the outer lane. So this is the matrix, shows the relative decrease in conflict as the CV penetration increased. So you can see, So you can see high penetration of CV is required to have more conflict reduction during the peak hour, and while with only 25 CV penetration, you can see vast conflict reduction during the less congested period, like pre and post peak hour. And the lane change conflicts were relatively small. The reduction in lane change conflicts were relatively small compared to the reduction in rear end conflict. So the PM period, we had like the more conflict more than AM period, because this period were more congested, but again, they were a relative decrease in the conflicts as CV penetration increased. In the matrix right here, it just shows the same pattern as I showed in the previous slide for the AM peak period. And here the market penetration was required, higher market penetration was required to achieve significant reduction. Quickly, the statistical analysis showed that for all period there were significant. Okay, again, I used the one-tailed t-test just to see if there were significant reduction between scenarios after increasing the CV market penetration, and the results from that statistical analysis shows that in all periods significant reduction was occurred, even for every 25 increment of CV composition. And for AM peak, PM peak, and post peak, this was the highly congested period. And for when the outer lane was blocked, there was significant reduction, and that was observed beyond 50% CV composition. And for AM peak, again for the same peak, for the same period, for the outer lane blockage and the inner lane blockage, significant reduction was observed beyond 50% of this reputation. Sorry. So the conclusion: more conflict reduction up to 98% from the matrix there. We have seen that was occurred during the lower traffic volume period with full penetration, and 50% of conflict reduction at 25% penetration of CV during lower traffic period. Another finding was during congested scenarios, for congested scenarios, high composition of CVs is required to achieve significant benefit from the statistical analysis. So here, up to 33% reduction was occurred with 75 penetration, and this is for congested period. So many conflicts were observed when the outermost lane is blocked compared to when the innermost lane was blocked. So these are the sum of the recommendation for the future study to see the effect of driver compliance and to investigate the effect of data loss on signal propagation in the CV environment.